Bismillahirrahmanirrahim. Welcome to my YouTube channel Technically Explained. In this video, we are going to solve the examination paper which was conducted today at Electrical Department UET Peshawar for the fall 2022. The paper consisted of 6 questions and the total time for the paper was 2 hours. The first question carried 10 marks and the other question carried 8 marks. So the total time was 2 hours, but if you know the basics, if you can uh, solve the paper, you can solve it within 1 hour also. So this was the paper. Question 1 was related to the basic concepts of op-amp. Question 2 was related to gain bandwidth product. So you have to simply put in the formula and then you can get the answer. Question 2 was related to the feedback topology, which was the voltage series feedback topology. Question 4 was from midterm, which was from JFET. So, and again, you can solve this question by your expertise. You do not need to know in-depth knowledge of JFETs or of any FATs. Just need to know the basics to solve this question. Question 5 was from 555 timer and question 6 was from the CMOS technology. So let us start solving. The question number 1 is related to op-amps. Let us solve this question number 1. Okay, so question 1 states that if V1 is equal to 1 volt and V1 is the voltage here, fine. If V1 is 1 volt and V2 is 2 volt, V2 is this voltage which is 2 volt, the op-amp circuit of figure 1. This is your figure 1. Find voltage at point A. So this is your A point. We need to find the voltage at point A. The B is voltage at point B, so we need to find the voltage at point B, and finally the V naught voltage. And I have also divided this into blocks to simplify things for you. Now first of all, we need to find the voltage at point A, which is VA. Now if you look at this amplifier, this is a inverting op-amp, and the output of this inverting op-amp, this VA, will be equal to minus the feedback resistor, which is RF, divided by the input resistor, which I am going to call R1, and then multiply by the V1. Fine. So this is your feedback resistor 6 kilo ohm, this is your R1 2 kilo ohm, and V1 is given to you, which is 1 volt. We are going to have VA is equal to minus 6 kilo ohm minus sign because it is an inverting op-amp, divided by the 2 kilo ohm, which is this resistor, multiply by the V1, and V1 is given to you, which is 1 volt. So this comes out to be VA is equal to minus 3 volt. So if you get this right, you get 3 marks in the paper. Fine. So VA is minus 3 volt. We have find the voltage at point A. Next is to find the voltage at point B. Again, if you look at here, we have again an inverting op-amp with the same formula. So VB is again minus because it is inverting op-amp. The feedback resistor, which is 8 kilo ohm, divided by this resistor, which is 4 kilo ohm, and multiply by V2. Fine. Now V2 is again given to you, which is 2 volt. So if you simplify this, you are going to get VB is equal to minus 4 volt. So we have find the VA and now we have find the VB, which is minus 4 volt. And if you get this right, you get 3 marks. If you get those two right, you get 6 marks. Fine. Now to find the V naught. Now if you can see over here, this is your summer circuit. This circuit basically adds the two inputs. If you can see over here, we have a summer, which is an inverting summer. So 5 kilo ohm resistor and 15 kilo ohm resistors are your R1 and R2, and again we have a feedback resistor for this op-amp for the block C, which is 10 kilo ohm. So this is our summer resistor, and we know that the output for this adder or summer is going to be equal to V naught is equal to minus RF, where RF is now this resistor. This is the feedback resistor. Fine. Divided by the R1. If you remember the formula, again R1, I am going to say that R1 is suppose this 5 kilo ohm resistor, because we have two resistors, so we are going to name it R1 and R2. You can name it as you want. You can name it as RA, RB, or anything else. So this is RF divided by R1 into the V into this VA, because this voltage is now apply over here, and we have VA is equal to minus 3 volt. So this is VA, and then we have again RF divided by the R2. Now R2 will be the other resistor. Then it will be multiplied by the VB, because VB is now applied as a voltage over here. So we are going to simplify this. Now V naught is equal to minus, now if you can see over here the feedback resistor is 10 kilo ohm. So I'm going to put 10 kilo ohm over here in feedback resistor, divided by R1. R1 I'm going to call the R1 to this 5 kilo ohm resistor. Fine. I'm going to say divided by the 5 kilo ohm resistor, multiply by the VA. Now we have already found out the VA, which was minus 3 volt. So I'm going to put minus 3 volt over here. And then we have the plus, again RF is your that feedback resistor, which is again 10 kilo ohm. And then we have the other resistor, and this other resistor is your 15 kilo ohm. So basically this circuit is your adder circuit. So this is your 15 kilo ohm, and then multiply by the VB, and VB is your, we have already find the VB, which is minus 4 volt. So I'm going to put minus 4 volt over here. So this is minus 4 volt. Fine. Now I just need to simplify this to get the output voltage V naught. So we are going to have minus, this will be 2, so this will be minus into minus 6, and then we have this thing, so this is 2 by 3 multiplied by minus 4, so this will be minus 8 divided by 3, of course the voltage. So we need to take the LCM. So because here we are going to have 1 over here, and so we need to multiply 3 over here and in 3 over here as well. If we take the LCM, because the LCM comes out to be 3, so we are going to have minus 18 minus 8 divided by 3 volt, and this comes out to be V naught is equal to 26 divided by 3 volt. This is your answer. And if you get this answer, if you solve this in a way, it is you are going to get 4 marks. So 3 marks for the VA, 3 marks for the VB, and the 4 marks for the V naught. So total 10 marks for this question. This is how we can solve the question number 1. Inverting op-amp, use formula for block A. Inverting op-amp, use formula for block B. And then this is your summer or adder circuit, and we use the adder or summer formula, and then we get the final result as 26 by 3 volt. Okay, let us solve question number 2. Question number 2 states that consider a feedback amplifier with an open loop low frequency gain of A is equal to, this is 10,000, A is equal to 10,000, an open loop bandwidth of W is equal to 2 pi 100 radian per second, and a closed loop low frequency gain of AF is equal to 50. Determine the bandwidth of a feedback amplifier. This is probably the simplest question in the paper, and it can be solved within few minutes. Now let us solve this. Okay, so we are given with open loop low frequency of gain of A is equal to 10,000. So this is basically your open loop gain. So I'm going to say that we are given that A is equal to 10,000. Fine. So we are given with gain without feedback is 10,000, and we are also given with gain without bandwidth, which is W is equal to 2 pi 100 radian per second. Now from here I can find the bandwidth. That bandwidth is equal to, I can say that W is equal to BW, I should say BW is equal to, and this is gain without feedback, that is equal to 100 Hz, because we know that omega is equal to 2 pi f. If we compare omega is equal to 2 pi f with this 2 pi 100, so 2 pi and 2 pi will cancel out, and you are going to have f, which is the bandwidth over here, as 100 Hz. And then we have the closed loop low frequency gain of AF is equal to 50. So we have gain with feedback, that is equal to 50. Now we know that according to the gain bandwidth product, according to gain bandwidth product of gain and bandwidth without feedback is equal to product of gain and bandwidth with feedback. So basically what do we need to find over here? What we need to find is that we need to find the bandwidth with feedback. So we need to find this BWF. This is the bandwidth with feedback. Fine. So I'm going to say that A is 10,000. It is multiplied by 100, and we have gain with feedback 50 multiplied by the bandwidth with feedback. This is bandwidth with feedback, that is equal to 10,000 multiplied by 100 divided by 50. This 0 will be cancelled out this, so we are going to have 1 and we are going to have 2 over here. So 2 multiplied by 10,000, that is going to give me 20,000 hertz. So this is the gain of the, so this is the bandwidth of the feedback amplifier, and that's what we intended to find out. So the bandwidth of the feedback amplifier is 20,000 hertz, and this is the answer to the question number 2. Okay, now let us look at the question number 3. Question number 3 states that calculate gain, input and output impedance for a voltage series feedback. Fine. So we have voltage series feedback topology, and we are given with A, that is minus 300, input impedance which is 1.5 kilo ohm, output impedance which is 50 kilo ohm, and beta which is the feedback factor, that is equal to minus 1 by 15. So this question intends to know that whether do you know that what happens to the input impedance in voltage series feedback, what happens to the output impedance in voltage series feedback, and what happens to the gain in voltage series feedback. Fine. So let us solve this. Okay, so this is question number 3. And now we know that in feedback, the gain decreases by a factor of 1 plus beta A. The gain with feedback will be equal to A divided by 1 plus beta A. And this happens in every feedback. Same is the case in voltage series feedback. Now first let us calculate the factor 1 plus beta A. So this factor 1 plus beta A, we are going to have 1 plus beta is given, which is minus 1 by 15. And A is also given, which is gain without feedback, which is minus 300. So this is equal to 1 plus 300 divided by 15, and 300 divided by 15 is 20, because 15 twos are 30 and 0 is over here, so I'm going to put 0. So 20 plus 1, we are going to have 21. So this factor 1 plus beta A has been found out, and that is equal to 21. So now gain with feedback, which is the first thing to find, that will be equal to A is your minus 300 divided by 1 plus beta A, and 1 plus beta A is your 21. So minus 300 divided by 21, this comes out to be minus 14.3. So this is your one of the part of the question. Next is to find the input impedance. Now we know that in voltage series feedback, the input impedance increases, and the input impedance increases by amount 1 plus beta A. So that's why we are going to have the formula Zi into 1 plus beta A, and this Zi is basically your Ri, and this is given to you, which is 1.5 kilo ohm. So what you need to do is that this is your 1.5 kilo ohm, and then we have the 1 plus beta A, which we already calculated, that is 21. So if you multiply those two, you get 31.5 kilo ohm. So the input impedance has been increased to 31.5 kilo ohm. And the next thing to find is the output impedance, ZOF. And now we know that in voltage series feedback, the output impedance decreases by amount 1 plus beta A. Again, output impedance is given to you. This is your output resistance or output impedance, which is 50 kilo ohm. So you need to just put the values 50 kilo ohm divided by the 1 plus beta A, which we calculated to be 21. So if you solve this, you are going to get 2.38 kilo ohm. Fine. So the gain has been decreased. If you can see over here, gain without feedback was minus 300, which has been reduced to minus 14.3. Input impedance has been increased, which was 1.5 kilo ohm without feedback, but now it's 31.5 kilo ohm. And similarly, the output impedance has been decreased by amount of 21, and this is your output impedance. So this is the solution to the question number 3. Okay, then we have question number 4, which was from the midterm. And believe me, though this question looks intimidating at the start, but this question is also very easy. And this question can be solved within 1 or 2 steps. So it says that we have an N-channel JFET, and that is biased by the potential divider method. So the DC biasing is voltage divider biasing. And it is desired to set the operating point at IDQ is equal to 2.5 milliampere and VGSQ is equal to minus 2.5 volt. So we are given the Q point for the DC analysis, which is the IDQ is 2.5 milliampere and the VGSQ is minus 2.5 volt. And we are also given the VDS, the drain to source voltage, as 8 volt. It says that if VDD is 30 volt, this VDD is 30 volt, R1 is also given, which is 1 mega ohm, R2 is also given, which is 500 kilo ohm. We need to find the value of RS, and we are also given the IDSS, which is 10 milliampere, is the maximum drain current, uh, and then we have also given with the pinch of voltage, that is VP is equal to minus 5 volt. So what we need to find is that we need to find this RS. Fine. So now let us find this RS. So okay, so this is that question number 4. Now this is basically related to the DC analysis. Fine. So we have the VGSQ, IDQ, and the other all the other parameters. So now first of all, we need to find this RS. Find the value of RS is unknown. First of all, what we need to do is that we can easily find the V2 over here. Fine. This we call the VG, which is the gate voltage, or the V2. We can easily find this. Now, this V2 can be found out using the voltage divider rule, because this V2, which is over here, this will be equal to, using the voltage divider rule, this will be equal to 500 kilo ohm divided by these two resistors, which is 500 kilo ohm plus 1 mega ohm multiply by this voltage, which is the VDD. Fine. This VDD is your 30 volt. So we are going to have V2 is equal to 500 kilo ohm divided by 500 kilo ohm plus 1 mega ohm, and 1 mega ohm is 1000 kilo ohm. Remember this. Multiply by 30. So when you solve this, you are going to get V2, because this will be 1 by 3, because 1 mega ohm is 1000 kilo ohm. So this will be 1 by 3 multiplied by this 30, and we are going to get V2 is equal to 10 volt. So once V2 is find out, this V2 is once this V2 is find out, that is 10 volt, we can easily find the RS. Because we have DC analysis, this capacitor is going to be open circuited. So what we need to do is to apply a KVL over here, and we can simply find this RS. So if we apply KVL in this loop, we are going to have V2 is equal to the VGS voltage, which is the gate to source voltage. Here this is your VGS voltage, plus IDRS, because here the IS current flows and IS is equal to ID. We know that IS is equal to ID. So now V2 is your 10 volt. So we have 10 volt, and we have VGSQ already given to us, which is minus 2.5 volt. I'm going to say that my VGS is minus 2.5 volt. And then we have the IDRS, and we are already given with IDQ, that IDQ is your 2.5 milliampere. So from here I can easily find the value of RS, 2.5 milliampere into RS. Now minus 2.5 volt, I am going to shift it over here. This will be 10 volt plus 2.5 volt, and this will be equal to 2.5 milliampere into RS. So 10 volt plus 2.5 volt is 12.5 volt. And so we have 12.5 volt is equal to 2.5 milliampere into RS, which means that RS is going to be, let me change the color because I don't like the red color. RS is equal to 12.5 volt divided by 2.5 milliampere, and this RS comes out to be 5 kilo ohm. And this is the answer of this question. So the question looked intimidating, but this was very easy question. What we need to do is that, because we are dealing with RS, we need to deal with this loop. So for that we need to find the V2. V2 can easily be found using the voltage divider rule. So I found out the V2 and then apply the KVL, and as a result I got the RS, which was 5 kilo ohms. Okay, so then we have question number 5. Question number 5 is related to the 555 timer. It says that consider a circuit with R1 is equal to 10 kilo ohm, R2 is equal to 10 kilo ohm, and C is equal to 1 microfarad. These are the external components. The 555 timer is working in which mode? Find the duty cycle and frequency. So we have 555 timer circuit given. We are asked that in which mode it is operating. So first of all, because if you see the connection, pin 2 and pin 6 are connected together. We have resistor R1 and R2 between the pin 8 VCC and the pin 2 and pin 6. We have resistor R2 between the discharge pin 7 and the pin 2 or pin 6. So this is basically your astable mode of operation. So the 555 timer is operating in astable mode of operation. First thing, the 555 timer, let me change the color. The 555 timer is operating in astable mode of operation. Astable mode of operation. Okay. Next is to find the duty cycle and frequency. Now because we do not have a diode connected across the resistor R2, so the duty cycle is greater than 50%. And for the greater than 50%, we have the formula for the duty cycle, that is equal to R1 plus R2 divided by R1 plus 2R2, and if you want to express in percentage, we have to multiply it by 100. So R1 is 10 kilo ohm, R2 is also 10 kilo ohm. So we are going to solve it and we are going to find the duty cycle. This is 2 into R2, so 2 into 10 kilo ohm is 20 kilo ohm. So we have 20 kilo ohm divided by 30 kilo ohm multiply by 100 if you want to express it in percentage. That is 0.66 multiplied by 100, which is 66.6% or 66%. Fine. I can write 66%. Let me remove it. The percent, let us not go into decimals, simply say that 66%. Fine. So we have found out the duty cycle. Next is to find the frequency. Again, the formula for the frequency is 1.44 divided by R1 plus 2R2 into C. Here C is your capacitance, so we have 1.44. R1 is 10 kilo ohm, R2 is also 10 kilo ohm. So 10 kilo ohm plus 2 into 10 kilo ohm. So this is your 30 kilo ohm, because we have 10 kilo ohm over here and 10 kilo ohm over here, and 2 into 10 kilo ohm is 20 kilo ohm. So we have, I'm going to write it, okay, 10 kilo ohm plus 20 kilo ohm, because this is 2R2 and R1 and R2 are both 10 kilo ohm. And C is also given to you. It says that C is equal to 1 microfarad. Micro is 1 multiplied by 10 raised to power minus 6. So we are going to have 1 multiplied by 10 raised to power minus 6 over here. Fine. So we have 1.44 divided by, let me adjust the screen, 30 kilo ohm, that is 30 multiplied by 10 raised to power 3 multiplied by 1 multiplied by 10 raised to power minus 6. Fine, I can write this as 1.44 divided by 30 multiplied by 10 raised to power minus 3. And I can write this as 1.44. This minus 3, when it moves to the numerator, it becomes plus 3. So this is 10 raised to power plus 3 divided by 30, which means that we have 1440 divided by 30. So we are going to solve it, and this comes out to be 48 hertz. So the frequency F is equal to 48 hertz. So that's what was required. Now this is one of the methods. If you want to solve it using the other method by finding the T on and T off, you can also do that. So for the second method, I'm going to write over here, this was the one of the method, and this is also a correct method. So you can also use the second method. Let me write over here second method. You can use the second method as well. The second method is to find the T on, T off, find the total time T, and from then you can find your duty cycle and the frequency. So first of all, your T on time. The T on time is equal to 0.7 R1 plus R2 into C. Fine. Here you can also write 0.693, 0.69, even 0.67. All are the same, but I have written 0.7 just to simplify. So we have T on is equal to 0.7. R1 is 10 kilo ohm, R2 is also 10 kilo ohm, so this is 20 kilo ohm, multiplied by the capacitance, which is 1 multiplied by 10 raised to power minus 6. Fine. So we are going to have T on is equal to 0.014 second, which means that 14 millisecond. Fine. So this is your T on time, and then we have the T off time. So your T off time is again 0.7 into R2 into C. R2 is your 10 kilo ohm, so 0.7 multiplied by 10 kilo ohm multiplied by 1 multiplied by 10 raised to power minus 6. And this comes out to be 7 millisecond. Fine. Because this is 10 kilo ohm is 10,000. This equals 0.07 second. That is 0.007 second, which is 7 millisecond. Fine. Now the total time T. The total time T, that is equal to T on plus T off. And that is equal to 14 millisecond plus 7 millisecond. Fine. Or I can write 0.014 plus 0.007. And that comes out to be 21 millisecond or 0.021 second. Fine. So this is your total time T. Now to find the frequency. Frequency is inverse of the time period or the time. So we have 1 divided by 0.021 second. And this comes out to 47.6 Hertz, which is approximately equal to the 48 Hertz as found by the method 1. Fine. If you look at here, using method 1, we find the frequency as 48 Hertz, and this is almost equal to the 48 Hertz. Second, time period or duty cycle. Duty cycle is equal to, in terms of time, that is T on divided by the total time multiplied by 100. Now again, T on is your 0.014 second or 14 millisecond. Fine. So we have 14 millisecond divided by the total time. Total time T is your 21 millisecond or 0.021 second. Fine. This is equal to 21 millisecond. So 14 divided by 14 millisecond divided by 21 millisecond multiplied by 100. And this comes out to be 0.66 multiplied by 100, which is equal to 66%. So this is method 2 of finding the duty cycle and frequency. Both methods are correct. So we have found out what was needed. We found the duty cycle and we also found the frequency. Using both the methods are correct. Okay, question 6 is to implement the following Boolean function using CMOS technology. The function is given to you A plus B. This is basically an OR gate. So what you need to do is to design a NOR gate and then followed by an inverter circuit or a NOT circuit. So that is going to give you an OR gate. So I'm not going to solve this because this is already provided to you in the slides. So I'm not going to try it again. So this was your paper for the final term exam. Hopefully you score well and hopefully you get good grades. Thank you and Allah Hafiz.